I got this question in email, and it's a good one to sort of evaluate and walk through because it covers a lot of principles. This is Chapter 6, so 6-23, and it gives us this question. The pulley system in figure, whatever this one is used to lift a 67 kilogram crate with this kind of setup of chains and pulleys and all that stuff. Assuming the mass of the chains, pulleys, and ropes are negligible, determine the force required to lift the crate at, here's the key, constant speed. And whenever you see that, you know that this is a dynamical equilibrium problem. So the sum of the forces in the vertical directions are going to be zero. So we want to find the force required to lift the crate and the tension in the upper chain and the tension in the lower chain. So we've got a lot going on here. We've got a chain here. I'm going to call that one has a tension T1 in it. I've got a chain up here. I'm going to say this has a tension T2 in it. And then I'm going to say that the rope here just has a plain old tension T. And we can do a bunch of analysis here to figure out what the tensions are in the various pieces of rope. And I actually think it's easiest to start out by considering the free body diagram of the crate. So if we have the free body diagram of the crate, then it has two forces on it. It has its weight, which is mg, and it has the chain tension, T1. And we know that the sum of the forces in the y direction have to be zero because the thing is not accelerating. And therefore, if we define our positive y direction to be upward, then we have T minus mg equals 0. Sorry, T1 minus mg equals 0. T1 mg equals mg, and that's equal to 67 kilograms times 9.81 meters per second squared, which is 660 newtons to the precision given in the problem. So that answers, I guess that's part C. Good job. On to part A. And to figure out part A, what I like to do is consider this pulley right here. So I'm going to say, let's see here, this was the block. And let's call this pulley 1. So pulley 1 is massless. And that means that the sum of forces on it are 0 because it's equal to ma. M is 0. Therefore, we're done. And we have two tension forces pulling up on it. There's T and T. Those are the rope tension from this rope and from this rope. And remember, in pulleys, the tension force acts on both sides of the pulley. So that's how we get two tensions there. We know that the downward tension is T1 in the chain. And so then we have 2T minus T1 is equal to 0. And therefore, T is equal to T1 over 2. And using the previous problem, that's mg over 2, and that's going to be 330 newtons. Same thing up here for P2. There's P2. And for pulley 2, we can go ahead and set up the free body diagram in the other direction, where we have the chain tension T2, and then we have two rope tensions pulling down, T and T, and this should look a little familiar. So we know that T2 minus 2T is equal to 0, and therefore T is equal to then T2 is equal to 2T. I've got to pick different names. Let's say that we could do that, only this time with like legibility. Yeah. Good stuff. So then we get 2t, and I happen to know what t is. It's t1 over 2, which is mg over 2. So this is equal to 2 times mg over 2, which is equal to mg. And that's also the answer for part C. So that's also 660 newtons. So we've done every part of the problem. The key point here is the pulleys with these ropes coming off on both sides of them have two tension forces from the rope that's threading them. And that's going to be a generic problem that we will see across a lot of our examples with pulleys. So keep that in mind when you see pulleys on the midterm. Okay, I think that's what we want to say. Good luck in your studying.